Okay, so we're going to, for this example, we're going to poll to find out who are Montanans planning to vote for in the election for U.S. representative. We're going to call, let's just say 100 registered voters. Real polls use a lot more people, but we're not going real here anyway. We're not going to actually make these calls. Okay, so real poll calls 100 registered voters. Suppose we know, or suppose that 48% plan to vote Williams. Okay, so that's what we know. Not 48% necessarily of this sample, but 48% of the people we're drawing this sample from. Okay, so 48% of the people we're drawing this sample from are planning to vote for Williams. Okay. And we start asking things like, what is the chance, or what is the probability that a majority of our sample votes Williams or plans to vote Williams? Okay, so what's the probability that a majority of our sample plans to vote Williams? The answers that this involves are examples of sorry, the data that comes from this are examples of a binomial random variable. Okay, the thing that makes this a binomial random variable is we have a set number of trials. Okay, let's just get another thing up here to look at. Okay. So this is binomial. Experiment is actually what it is. So we have to define the binomial random variable. So this is what's called a binomial experiment, this poll. There is a set, in this case 100, number of trials. And a trial, for our sake, is essentially a yes-no question. Okay? And in this case, what we're talking about is the same question repeated to 100 different people. So there's this set number of trials. There is a well-defined success on each trial. And in our case, the question we're asking, that success is Williams. This is not a political statement to say that Kathleen Williams is better or Greg Gianforte is better. It's merely a set of success is what we're counting. So if we were counting the number of times a respondent said Greg Gianforte, that would be our so-called success. Okay? It has nothing to do with whether it's a good outcome or not. It's just a matter of, it's the thing we're counting, and it's well defined. You can tell whether it happened or not, yes or no. And you're basically counting up yeses. There is a fixed probability. P, notice my P is a lowercase p I'm choosing here. Because this problem, unfortunately, little p's and big P's are going to float around within the same space. And we just got to get used to that. It's not much of that, but it's just, yeah, it's to the extent that it's there, we realize we're thinking about two things. Of success on each trial. That means there's this 48% in this case chance that any single person we contact is going to be a Williams voter. And the first person is 48%, second person it's 48%, third person it's 48%. It's a set. Okay? It's trials are independent. That is, knowing that the first person wants Williams does not affect the probability that any other person wants Williams. These observations don't matter based on each other. And so the key error that people tend to think of is, let's say we're on the phone, and let's say we get a streak, because it can happen. Call up someone, who are you voting for? Williams. Call another person, who are you voting for? Williams. Keeps going, Williams, Williams. And we maybe had 6 or 7 Williamses in a row. It's real tempting to think, oh, we're due for a Jan 40. We're due for another answer. But that's not how independent trials work. Independent trials mean maybe you'll get a Jan 40, maybe you'll get another Williams. 48% chance you get another Williams. Okay? So, we've got a fixed number of trials, well-defined success, well-defined probability of success on each trial, and the trials are independent. And the problem then is about counting up the S's. Okay? So this X is our number of successes. X is a binomial random variable. With n equal 100. Why n equal 100? Because n is the letter we're going to use for our number of trials. And p, little p again, equals 0.48. Because I've told you, in this case, to make the problem a little bit easier to adjust, usually what they do is they're trying to, what you'll see this is you'll read a study where I'm just noticing all the people on the phones this morning. It's driving me batty. Okay. All right, reset. So X is a binomial random variable. With n equal 100, p equals 0.48. And being able to answer that original question, say, what is our probability that 50% or 50, in this case of a 100-person sample, of our people want to vote for Williams. To ask a probability question like that about X requires us to know that it's not just any old random variable, it's not just any old discrete random variable, it is a binomial random variable with n equals 100, p equals 0.48. By the way, there is notation you'll see, a shorthand, X is distributed as, let me find the tilde button, is distributed as, capital B, binomial distribution. First parameter I write down, the first number I write down, 100, that means n is 100. Second number I write down, 0.48, that means my success probability is 0.48. Okay? So that's going to be the shorthand we use. And then what we are here in this case, okay, we want to find the chance that X is greater than or equal to 50. We go to get this, we can't just get it in our head. There is a formula that you could conceivably use, but we aren't going to go there because it's rather hideous looking. We're going to assume we do things on the computer. So the first bit, actually, since I told you guys that we are not going to worry about getting StatCrunch, I'm going to first show it on how to get it somewhere else. I think easier than going to Excel would be to go into the search engine and look for binomial calculator. Binomial calculator. When I look for binomial calculator, it takes me to a place, among others, StatTrak. Okay, there's several of these options here. I'm just going to go right to the one called StatTrak. Okay, which is a whole series of different things, not just the binomial calculator, a resource on learning statistics. Okay, so if we give it certain pieces of information, it's going to tell us what we want to know. And what we wanted to know, we decided, was namely, this shorthand stands for the probability of X greater than or equal to 50, or X is this thing that is distributed binomial random variable as a binomial random variable according to the binomial distribution, n equals 100, p equals 0.48. Okay? So, success probability on a single random variable, that's your little p, 0.48. That probability is going to be about a single random variable, number of trials, or of a single trial, that is. Number of trials in this case is going to be 100. And our number of successes is at least 50. We're just going to put the number 50 in here, and then we're going to pick off which one of these answers is the one we actually want to use. Okay? So I hit the answer, hit the return button, the enter button, and I get all sorts of items here. And what I want is the probability of X greater than or equal to my little x, which I defined here as 50. So this is the last row is what we happen to want in this case, because that says we're looking for X greater than or equal to whatever I put in that box up there. Okay, and that is 0.38 is the chance of getting at least 50 of these people saying Williams. Now, that's kind of, that makes some sense, I guess, because we got as a population we're pulling from, we're a minority, 48%, a large minority, want Williams. And so when we take a poll and try to figure out for ourselves if that's what's going on, the chance of us getting 50% or more, yeah, there's a good chance of it. You know, there's about 38% chance of it happening. Okay? And so there is our answer. Okay? What is the probability that the majority of our sample votes Williams? Probability of X. Uh-oh. Okay? And I'm just going to draw in here the greater than or equal to symbol. Okay? So there's an example of a binomial random variable. So the things you got to get used to in terms of reading up the problems is picking out what is our variable, what is our n, what is our x, and our p, little p. And then here's where capital P flies in. Is capital P is talking about a probability of a certain event in the entire binomial experiment. In the all 100 trials combined, we're looking for a certain thing to happen. What's the chance of that happening? That is when that big capital letter P gets used. When that small letter P gets used, it's talking about an individual yes-no question, an individual trial. So what's the probability of getting a yes on a single trial? 48%. That's little p. Okay. All right, let's pull up another example. Actually, I'd like you to do, let's go to page 269. That's your homework. 269 is your homework. I'd like you to do it in here, and then we'll talk about it either at the end of the time this time, if you guys have finished it, or at the beginning of our time next time. So we're going to do do this homework assignment instead, and just see if you can get up, because there's a situation, and you want to read and pick off what is that definition in words. What is that symbolic definition, like I did on the screen? What are the possible values that X could be equal to? Constructing what's called the probability distribution function. We ordinarily won't make a table like this for binomial random variables because we use the computer to calculate it. We can go through each of the possibilities of X and use the computer to come up with a P of X. Okay? So I want you to go through the next 25 minutes and answer these, and then we'll talk about them at the beginning next time, okay? At the beginning of next time.